Swayam Prabha. Digital India. Educated India.
Welcome back. So, in the last lecture we started discussion on shear strength of soil, and there we have seen that how you can get the formulation for Moore Coulomb failure criteria, and all those things we have derived, all those expressions rather, and then basically we started the laboratory experiment on the determination of shear strength. The first thing we took over, that is direct shear test, and there basically we talked about two different types of say test. One is a stress control test, another one is a strain control test. So, in the stress control test, the shear force is applied in equal increments until the specimen fails, whereas in strain control test a constant rate of shear displacement is applied to 1/2 of the shear box. So, those things we have discussed, and basically there is some advantage of stress control test. The advantage of stress control test is that in the case of dense sand, peak shear resistance, that is at failure, as well as lesser shear resistance, that is at a point after failure called ultimate strength, can be observed and plotted, right. So, we have seen that because in case of dense sand you will be getting the shear stress versus shear displacement, I mean that plot. If you plot that curve, basically you will be getting initial increment, then it will reach to the peak, and then it will fall down, and it will be becoming constant at higher strains, I mean shear displacement, right. So, basically in case of strain control test you can capture the whole say stress strain behavior for the dense sand, whereas if you go for stress control test, after reaching the peak, when the stress will be falling down, that part you will not be able to capture, because in stress control test you control the shear stress, right. You control the stress, and basically and you go to the progressive failure of the material, right. So, these things we have seen in the last lecture. So, basically if you look at this figure, so in stress control test only the peak shear resistance can be observed and plotted. So, in case of stress control test, basically what you do, you control the stress, that means some equal increment of stress you are giving, and you are observing the strain, right. So, in this process basically you will be able, because you are continuously increasing the stress. So, in this process you can maximum reach the peak, right. After peak, that means post peak part you will not be able to capture, because you have the control to increase the stress incrementally, right. So, in that process you will not be able to capture the post peak part, and that is basically the disadvantage of the stress control test. So, in stress control test only the peak resistance can be observed and plotted. So, you will be getting, so in case of stress control test you will be getting the plot something like that. So, you will be getting up to peak. Okay. So, the post peak part is not possible from the stress control test, right. So, compared with strain control test, stress control test probably model real field situation better. So, though in case of stress control test we are not getting the post peak behavior or the post peak say response, however, the stress control test is more towards the actual field condition. That means, say in case of what actually you do in any geotechnical structure, you generally say if you are placing the structure, say suppose if you consider a building construction. So, what you do, you place the foundation, and on top of the foundation you place the ground floor, first floor, second floor, and so on, right. So, what you are doing, you are just increasing the load, and that increment of the load eventually will cause the increment of the stress. So, basically in the real life, or you can consider some dam construction or embankment construction, you do not consider the dam overnight, right. So, basically what you do, you go for the first lift, then you go for the second lift, then you go for the third lift, and so on. So, in this process of incremental stress, basically you are increasing the or you are controlling the stress, right, in the soil. So, that stress control test is more associated with the actual field condition rather than the strain control test, where strain control test basically what you do, you control the displacement. So, that displacement control is not really happening in the field in the actual life. Now, in loose sand, so now we are going to discuss this stress strain behavior for loose sand as well as the dense sand. So, in loose sand, the resisting shear stress increases with shear displacement until a failure shear stress of tau f is reached. Okay. After that, the shear resistance remains approximately constant for further increase in the shear displacement. So, that means in case of loose sand, so this is your loose sand behavior. So, in case of loose sand, as you go on increase the shear displacement, you will be getting the increment in the shear stress. So, something like that, and then you will be reaching here. So, this will give you the peak shear resistance, that is tau f, and beyond that this will be becoming almost constant, right. So, this is the typical behavior for the loose sand. Whereas, in case of dense sand, the resisting shear stress increases with shear displacement until it reaches a failure stress of tau f. This tau f is called the peak shear resistance. So, as you increase the shear displacement, you will be getting the increment in the shear stress, okay, and you will be reaching the peak, that is nothing but your tau f, and it is known as peak shear strength. So, you will be reaching the peak, and then basically after failure. So, if I say this is when it is reaching the peak, at the time I am initiating the failure, if it is so, then after failure stress is attained, the resisting shear stress gradually decreases as shear displacement increases until it finally reaches a constant value called the ultimate shear strength. So, post peak region, that means after the peak, that means after the failure, basically you will be getting the reduction in the shear stress. However, the shear displacement is continuously increasing, and ultimately you will be getting the constant constant shear stress with say increment of the shear displacement, and that is known as ultimate shear strength. So, you are getting two regions for the dense sand. One is your peak shear strength, that is happening at the failure, and another one is the ultimate shear strength, that is happening at a large amount of shear displacement. Now, it is important to note that in dry sand, if you consider the dry sand, right, completely dry sand, there is no water at all. So, sigma is nothing but the sigma prime, that is the total stress must be equal to the effective stress, because only water will cause the difference between the total stress and the effective stress. If water is not there at all, then the total stress must be equal to the effective stress, and C prime, that is the cohesion, that is the effective cohesion, must be 0. So, if you can see this thing, if you take say cohesion, nothing but it will try to stick the material. Okay. So, in case of say dry sand, okay, you might have seen that all the particles I can separate out, right, all the grains you can separate it out. So, basically the cohesion is not there, only the angle of internal friction is present in the dry sand, right. So, basically if you try to plot this behavior for the dry sand from the obtained from the direct shear test, basically the failure envelope for the dry sand will look like this. So, basically along this y axis you have the shear stress, okay, at failure, and this is along this axis you have the effective normal stress. Okay. So, that means basically in the direct shear what you do, you apply some constant normal stress and then you shear it till the failure, right. Once you reach the failure, you stop the test, or if you want to further extend the test to get the idea about the ultimate strength for the dense sand, then you can go further, but in case of loose sand it will be constant. So, the once you reach the peak strength, that is tau f, that is the failure shear stress, that means nothing but your shear resistance or the shear strength. So, that is your shear stress at failure. So, for a constant magnitude of your normal stress, you are getting some shear stress at failure. So, this combination, for each combination you will be getting say some individual points, right. So, these points are nothing but at different normal stress you are doing this, you are obtaining this failure shear stress, right. So, similarly then basically with these data points if you draw a line and you know this is your linear relation, the Mohr Coulomb failure criteria is considered or is assumed as linear for the most soil mechanics problems. So, therefore, your tau f, so tau f is equal to sigma prime tan phi prime, as your C prime is 0. Already we have talked that C prime for the dry sand is 0, therefore, no cohesion. So, the failure envelope must pass through the origin, and therefore, the relation, I mean you have the relation for, I mean the general relation is, this is your general relation. So, if this becomes 0, then you have the remaining part, that is sigma prime tan phi prime, and that is written here, right. So, tau f, that is the failure shear stress or shear stress, rather shear stress at failure is equal to sigma prime, that is the normal stress, effective normal stress applied on that particular material, I mean soil, okay, dry sand, into tan phi prime. So, that means basically what you will get from the direct shear test, that means after performing the direct shear test you will be getting this line, right. So, this line you can establish after performing the direct shear test. So, once you get this line, you measure this angle. So, this angle will be your phi prime, okay, which will give you the shear strength, that means the angle of internal friction, and that is nothing but the strength parameters, right. So, you have two shear strength parameters, one is C, another one is phi. So, for dry sand C is 0, so you have got phi. So, now you can define the strength and you can develop or you can establish the constitutive behavior for that particular sand. Now, for dry sand, so already we have seen, so tau f is equal to sigma prime tan phi prime, therefore, phi prime is nothing but tan inverse tau f by sigma prime. So, after establishing this line, you can get the inclination of this line with the sigma axis, and which is nothing but phi prime. So, phi, now you can use this phi prime for your design purpose. Now, for example, though it is not within the scope of this course, however, for designing any kind of, say, if you design some foundation, if you design some retaining structure, if you design some embankment, and if it is made of, say, dry sand, say for example. So, basically you need this shear strength parameters phi prime to design that. So, if you want to find out the bearing capacity or the carrying capacity of the foundation, if you want to find out the stability of the slope, or if you want to find out the stability of the retaining structure. So, all those things basically are the function of this phi prime. Okay. So, this is very important parameter which you can find out from your laboratory experiment, that is direct shear test for the dry sand. Now, it is important to note that in situ cemented sands may show a C prime intercept. So, it is not true that all the times the sand will show C prime equal to 0. So, if you get some in situ cemented sand, okay, some very stiff kind of sand or the cemented sand, okay, that is not exactly the dry sand, or you cannot take out individual, or you cannot separate out the individual grains. So, in that situation sand may exhibit some C intercept. That means, in that situation your tau f is equal to C prime plus sigma prime tan phi prime, and the failure envelope will not pass through the origin, rather it will have some intercept which is nothing but the cohesion on the y axis, that is along the shear stress axis. So, some inherent shortcomings. So, direct shear test is having some inherent shortcomings, and that you must know. So, what are the different shortcomings? So, in case of, so this is your direct shear test mold, right, this is your direct shear test mold. So, basically what you are doing here, first let me go through, or let me read this statement. The reliability of the results may be questioned because the soil is not allowed to fail along the weakest plane, but is forced to fail along the plane of split of the shear box. Now, basically what is happening? So, when you are placing this sand, so this is your sand, right. So, this is your sand, right, or this is the soil sample rather, okay. It could be sand, it could be clay, whatever, I do not mind, but the thing is this is the soil sample. Now, in this soil sample basically you are forcing the soil sample to fail along this surface, because along this surface only the boxes, two halves of the box, shear box will move related to each other, right. So, you are forcing the soil, or you are telling the soil, you are insisting the soil that you must fail along that plane, which may not be true, right. You may have the weakest plane which is lying here. So, basically you are missing that weakest plane, because you are forcing, you are not identifying the weakest plane, and soil will be having the tendency always to fail along the weakest plane, because I mean it is obvious, right. So, if you if you carry some load, or if you are taking some stress, right, or anything. So, whatever organs is weak for you, right. So, that organ will fail first. So, this is a similar kind of analogy you can draw for the soil. So, if this is my weakest plane, the soil will train to fail along the weakest plane, which I am missing in the direct shear test, because in direct shear test we are imposing the failure surface, or we are forcing the soil to fail along this surface, which is predefined, right. So, I am defining the failure surface, rather soil should tell me that this is my weakest plane. So, I must fail along that plane. So, that kind of information I am not getting from the direct shear test. That is one of the biggest shortcoming in the direct shear test. I hope you have understood that. Now, the shear stress distribution over the shear surface of the specimen is not uniform, right. So, basically what is happening? So, suppose in the first instance you have the two boxes like that, right. When you are pushing, okay, the one box or one half of the box with respect to the other half, basically what is happening in the next configuration. So, this is your configuration say 1, that means at the initial stage or the starting of the test. Now, in the configuration 2, basically you are getting some relative movement, right, of the two halves, right. So, these are two halves of the box, direct shear box. So, basically now, so this is your say configuration number 2, that means when the test is progressing. So, you are getting this kind of situation at each and every point. So, at the initial stage, when you applied the shear stress, that shear stress distribution, right, over this area, right, agreed. So, whatever shear stress, whatever pushing you are doing or you are applying to the soil, so that will be acting on this area. So, total area will be participating in the resistance of the shear stress. However, when the stress is progressing, that means at that time you will be getting this much of area, which will be taking care of the shear resistance or taking care of the externally applied shear force, right. So, that means the shear stress distribution. So, if you consider the shear stress distribution over the area, the shear stress distribution over the shear surface. So, this is your shear surface of the specimen is not uniform, right. So, as you are applying the shear force, you are getting some reduction in the shear surface, and that shear surface reduction will not guarantee, right, the shear stress distribution is uniform. So, that is another biggest disadvantage of direct shear test. So, I hope that you have understood the direct shear test concept. So, this is, however, with these two shortcomings, still people use direct shear test, and this is a very handy test, okay. And no matter whatever shortcomings are there, but direct shear test results have been found that if you design something based on these direct shear test results, those things will function properly, right. It has been seen from the experience also. Now, coming to the next type of say laboratory experiment, that is triaxial shear test. So, a soil specimen in this basically test, what we consider some cylindrical soil specimen. The soil specimen of 38 millimeter in diameter and 76 millimeter long. Generally, we consider this kind of soil specimen. So, we have to do some test say exercise, okay. So, to prepare the sample. So, basically this sample should be made of some cylindrical sample, something like this, okay. So, 38 millimeter diameter and 76 millimeter height, okay. So, this kind of cylindrical sample we prepare, okay. Some mold is there, and you have to take really proper care to find out or to obtain this kind of sample. The specimen is subjected to confining pressure by compression of fluid. That means, this specimen, so this specimen whatever you are getting, and I will be showing the triaxial test setup in the next slide. So, basically what you do, you place the soil sample and you apply the confining pressure, that means all round some pressure you apply, okay. Some radial pressure you apply, radial as well as axial, all those things. I mean, in all directions you will be putting same amount of pressure by compression of fluid. Generally this fluid is water. So, you put water inside some chamber, and in that chamber you put this say soil sample, and because of the soil, I mean water pressure, that pressure will be exerted on the soil specimen. To cause shear failure, now under this hydrostatic, as you know from your mechanics background, that under hydrostatic pressure the specimen will not fail, right. So, to cause the failure, to cause the shear failure in the specimen, one must apply some axial stress through a vertical loading ram, and that is called as deviated stress, right. So, we will come to that point. So, basically we are getting two different kind of say pressure, application of pressure, one is the confining pressure, another one is the deviatoric pressure. Okay. So, basically this is your typical triaxial say test setup. Here actually this is your soil sample, okay. The specimen enclosed in rubber membrane. So, basically the soil sample will be enclosed in a rubber membrane. So, that means you are putting the soil sample inside a rubber tube, otherwise the water. So, because this the whole chamber is filled with water, as I told you, right, and this other, I mean if you do not put the rubber gasket, right. So, rubber membrane. So, basically water will try to wash the soil sample or try to enter the soil sample. So, that should be avoided. So, this water is only allowed to apply pressure on the soil specimen, that is the only function of this, I mean cell water, right, cell fluid. Okay. Now, this rubber membrane, okay, will be tightened by this rubber ring at the top as well as the bottom. Okay. Now, you apply pressure with some. So, this is the pressure, I mean this is the pressure gauge which will measure the pressure, how much pressure is applied inside the cell. So, to cell pressure control, so that means through this line, through this pipe actually you control the cell pressure. That means you can increase the cell pressure or you can decrease the cell pressure. Cell pressure means the water which is put inside the say I mean cell or the inside the chamber, right, that chamber, that water will be under some pressure. So, you can increase the pressure or you can decrease the pressure, and that is known as cell pressure, right. And now, once you apply the cell pressure, the soil sample will be experiencing the cell pressure from all in all the directions, right, in the radial direction as well as in the top direction, bottom direction, all directions it will be experiencing the cell pressure. Now, the soil specimen will be having the porous disc at the top as well as the bottom to facilitate the drainage, right. So, under this process the soil specimen may consolidate, and this consolidation will be facilitated by the drainage of the water from the soil specimen, and that drainage will be taken care of by this porous stones. Okay. Now, this is your top cap, this is your say these pipes, these two pipes, basically they will be taking care of the pore pressure determination, right. So, basically when you will be applying the load, okay, I mean deviatoric load or the deviatoric pressure, basically the water will be trying to draining out from the soil specimen, and that will be collected through these pipes, and they will be connected to some pore pressure measurement arrangement, and that will give you the pore pressure, how much pore pressure is getting dissipated, something like that. Now, so once you apply the pressure in the water, that is cell water, right. So, that cell, I mean pressure will be enhanced, cell pressure will be increased. Now, under that situation under that condition basically soil will not fail, because you are having the hydrostatic pressure all round, right. So, to fail the sample basically you need to apply some axial load through this piston and through this loading ram, and this axial load is known as the deviatoric stress. Okay. And when you apply the deviatoric stress, then only soil will be under some shear failure mode. Okay. Now, what are the different types of triaxial test? The first one is consolidated drain test. Okay. We will come to these tests individually and we will discuss the pros and cons of each test, and we will see that what are the different procedures you have to follow to obtain these different types of triaxial test. So, first one is consolidated trend test. Generally, it is defined or it is represented as CD test, okay, in soil mechanics. Then consolidated undrained test, and that is known as CU test, and unconsolidated undrained test, that is UU test. Okay. So, basically we will discuss all these tests separately, and then we will see that I mean what test should be done at what condition and what test will be giving you better result, and I mean under what situation. Okay. So, these things we will be seeing in the next class. So, I will stop here today. Thank you very much.